All right, section 4.1 is going to involve some notation that you've probably seen somewhere before, but you probably haven't used it extensively. We're going to use it for a couple of sections anyway, and the notation is the sigma notation. And this is the sigma notation. It is talking about how we add up, or a description for how to add up a bunch of terms. So if we have terms A1 to AN, there's nothing special about them. They're just a bunch of numbers, okay? So if we wanted to add up a whole bunch of numbers together, a way to write that in a condensed form is to use this summation notation, this sigma. Now that sigma notation, you'll see after it has A with a subscript of I. That's just saying I'm going to add up all of these terms together. The terms are going to start at I equal to 1, so you see the first subscript is 1. And they're going to end at the term n, whatever that number is, and they end at n over here. You would not have to start at the number 1. I'll show you what happens when you don't, when we're doing some of the problems. But most of them do start at the number 1. The I is called the index of the summation, and the A with a subscript I is actually just the ith term. So if you had A with a little 5 down there, it would be the 5th term in the sequence. That's all it is. Okay? We call the 1, the number at the bottom, the lower bound, and we call the number at the top, it's in on the screen, the upper bound. You will also see, and it's more of a formatting issue than anything else, you will sometimes see it, and you'll see this in your notes, where it does this. Instead of putting the n on top and the I equal 1 on bottom, it actually looks like it's sort of out to the side. It's just a formatting issue with Word that does that. It means the same thing. Okay, any questions so far? Okay, so we're going to do an example. The example on this one actually shows I starting at 1, ending at 6, and 3i minus 2 is the a sub I term. It's just an equation. That's all it is. What this tells you is that we're going to add up all the terms that start out with I equal to 1 and end with I equal to 6. So the first way I want to show you how we do this, and you're going to have 2 problems, I think it's 2 problems in your homework that are going to have you do this, is we're just going to plug the number in. So we're going to take 3 and plug in the number 1 minus 2, and that would give me what? 1. And we're going to find a sub 2. So that's 3, plug in the number 2 minus 2, which gives me 4. We're going to find a sub 3. 3 times the I equaling 3 minus the 2, which gives me 7. A4 is 3 times 4 minus 2, which gives me 10. Now we could find A5 and A6 using this as well. The other thing that you might notice at this point is there's a pattern going on. 1, 4, 7, 10. What's the pattern? Plus 3. Do you know why it's plus 3, Taylor?
No.
Okay. Anyone else see maybe?
Moving up by multiplying I by 3.
That's right. There's a multiplication factor here, so it's a 3. Because you're multiplying by 3 every time, that's actually changing it by a number of 3 every time. If you happen to notice a pattern, it would be perfectly fine for you then to use the pattern to write down the next 2. If you didn't, it would be fine. You're going to get the same thing either way. If I use the pattern, what comes after 10?
13.
And then after 13? 16. All right, this notation actually says that I'm going to take all these terms and add them together. So I have 1 plus 4 plus 7 plus 10 plus 13 plus 16, which gives me what? Take a minute, add those up, or grab your calculator. You're probably going to want your calculator out in a minute, so if you don't have it out already, you might want to grab it. What is it? It's bigger. It's bigger. What'd you get, Jason? 51 is correct. Yeah, it is 51. All right, so a couple of things let me sort of make note of. This started at I equal to 1. Let's say instead of starting at I equal to 1, it started at I equal to 3. How would that change the problem?
We take out
We would do what?
take out the pairs of 1 and 2.
Okay, so we wouldn't have the A1 or the A2, right? The subscript just tells us where we start. So if this started at A equal to 3, we would start this listing out with A3, right? That's the only difference. So wherever the denominator, wherever the bottom lower bound tells you to start, that's simply where you start your I values. Okay? Now this would be great if I only have 6 values to add up, right? It's not bad. What if you have 106 values to add up? Not good, right? Not good at all. Or what if it was just more complicated, right? What if it had some square roots involved, or what if it had powers that were bigger than, and this is just a linear, right? 3i minus 2, and at some point we noticed a pattern, right? What if it had something much more complicated in that a sub I spot? Well, we might not want to actually list out, that many terms or those complicated of terms. So it would be handy if we had some way to do it in a quicker fashion. We do. What we're going to do is we're going to look at some summation formulas. There are 5 of them. Your book kind of condenses it into 4. I expanded it a little bit because I think it looks a little bit cleaner. Notice all of these formulas do start at I equal 1. It's actually really important. Did you have something in your calculator that's helpful, Jason? Yeah, there is a summation in your calculator that's useful too. These do all start at I equal 1, all right? So I'm going to have to deal with when it starts with I equal 4 a little differently, or whatever it is that we're going to work with. I think I have an I equal 4 example that we're going to do. It's different than in your notes. I'll show you when we get there. But please make note that these do start at I equal 1 in order to do these rules. All right, so here's the deal. The first one is just a constant, right? I just have a constant. So let's pretend like this is the number 6. C is 6. So if C is 6, and you were writing out, like this just said, I'll erase this in a minute, but let's just say this is said I equals 1 to n of 6. What would A1 be? 6, and A2 would be 6, and A3 would be 6, and we keep going all the way down. We're supposed to add all these numbers together a whole bunch of times, and it's the same number, and you learned a shortcut to doing that in 3rd grade. Do you remember what it was?
Multiplication.
Multiplication. So multiplication is just repeated addition, right? This would be 6 times n, however many terms you have, right? So this is Cn. That is the only one I'm going to justify for you. The rest of them are in your book if you're interested. So this is the formula. It's just Cn. So if you just have a constant that you're wanting to sum from 1 to 12, then it would just be that number, that constant times 12. All right, on the next one, we have I. So this is like just having the numbers themselves. So if I were to use this one right here and I were to plug in I equal to 1, I would get 1. And if I were to plug in I equal to 2, I'd get 2. And I equal to 3, I'd get 3. And I equal to 4. So this is just all of the whole numbers, right, from 1 to wherever I stop added up. Agreed? A mathematician named Gauss is one of the people who talked about how to do this in a concise way. The shortcut, if you will, to doing this is to recognize that this is the formula that will work. You can take however many terms you have times exactly 1 term more and then divide by 2. So if n stopped at 12, this would be 12 times 13 over 2. Okay, it's all based on what's on top of that lower upper bound. Next one, number 3, would be squaring all the terms, right? So this would be like having 1 squared plus 2 squared plus 3 squared plus 4 squared, sums of squares. And it has a formula as well. It starts out looking very much like the formula we just had, n times n plus 1. But then you multiply it by 2n plus 1, and the result is divided by 6. In case you're curious, there are closed forms. This is a closed form that we're writing on the right-hand side. There are formulas, if you will, for I cubed and I to the 4th as well. They're in your textbook. They're within the homework section of your textbook, not within the notes section or whatever at the beginning. So there are other ones we could do. This is enough for what we're going to be working with, these basic 3. The next slide, and it's further on your list, 4 and 5, are simply talking about ways to combine things. So if you'll notice on number 4, what we have is we have a constant times some value, right? We've seen the idea of having a constant multiplier before. We saw it both back in chapter 2 when we first did derivatives, and we saw it in section 4.1 when we did antiderivatives. What would be so nice for this to be? Right. The same thing as number 2, or at least some version of it, where you've got stuff whatever the stuff looks like, either of these, actually 2 or 3, you've got whatever your formula is, but then just times the c when you're done. Constant multiplier rule works that way for derivatives and antiderivatives, and it works that way for summations as well. So in essence, you can almost have this feel that you're taking c times whatever the sum would have been had the c not been there anyway. So you have the summation, and then you can multiply the c when you're done. That's what we do with derivatives, right? You take the derivative and you multiply by that constant. You take the antiderivative and you multiply by that constant. We call it a constant multiplier rule when we've used it in those senses. We've seen number 5 with derivatives and antiderivatives as well. It works the same way here. So what should this look like?
The summation A to I plus the summation B squared.
That's exactly right. We can do those two summations separately. Just like our derivatives and antiderivative rules allow for us to do. All right, you ready to see how one of these works? All right. This one only goes up to 16. It wouldn't be horrible to do, right? I mean, we'd only have to write out the first 16 terms. We could do that. But if we could do it in half the amount of time, I totally pulled that number out of just thin air. But if we could do it in less time some other way, we'd like to do that instead, wouldn't you? Sure. And we can do that using several rules. So first of all, you notice there's 2 terms with a subtraction sign between them. It's not an addition sign, but it's virtually the same as number 5, right? And it is. It works the same way. So we can separate the 5i from the 4 by doing 2 separate summations. The 5 is a constant, so that 5 can be plucked out and put in front and treated as an sort of as an afterthought or an after effect. So this can be rewritten as a 5, the summation from I equal 1 to 16 of I, minus the summation from I equals 1 to 16 of 4. And I do want to see that written out. That's showing that you've used all the properties, and then you're about to show how you're going to use the properties to find those individual summations. What property is this first one? It's property number, well, 2. I used properties 4 and 5 to split things apart. I already used those. But I'm going to use property 2 to actually find the summation of the I equals 1 to 16 of I. So I'm going to take a step. I'm going to write it a little bit differently. There's a couple of ways you could do this. But the property says I should have n times n plus 1 over 2. And I'm just going to note to the side that I know that in this problem, n equals 16. So you can plug the 16 in as you go, or you can plug it in a separate step secondly, like I'm about to do it. It just depends on how comfortable you are with the notation. What property is the second one here? That's property number 1. It's just a constant. Property number 1 says I should be able to take that constant and multiply it by n. And again, n is 16. So my next step is going to be putting that in. So I have 16 times 17 over 2 minus 4 times 16. Now let your algebra do a little, or your calculator do a little bit of multiplication and subtraction for you.
Is it okay if we split them up into 2 separate deals and combine them at the end? Or do you want to do
Yes,
them all
you
at
could do
once?
it that way. That'd be okay. What do you get?
616.
616. Do I have a second on that? Excellent. It's like a board meeting. There's a first, there's a second, and they match. 616. Okay, any questions on that? Yes, Samantha?
How do you know the first one is the second property?
Because it matches. It looks just like it. So you're just looking to identify which one it looks like. The second property has an I here, and that was exactly what ours had, just plain old I. The only difference is that instead of having n on top, we had 16 on top. That's why we identified that n is 16. Okay, so it's a matching exercise. Yeah.
When we answer these, do we put the number, or do we need to put that it's?
The final answer, well, each of these steps, the way that I wrote mine out, is equal to the one before. So the answer is 616, yes. Now, if you do it in separate steps like what Taylor was mentioning, you might have it written a little bit differently, like you might have broken this apart and said, okay, well, I find the summation from I equal 1 to 16 of I, and you did your little bit of work or whatever and found out that this result was, what did you find, Taylor?
680.
680. And then you found that the summation from I equal 1 to 16 of 4, and what did you find after your work on that one, Taylor?
64.
64. So then coming back to the original problem, you would have had something like 5 times 680. Oh, you did the 5 times it as 680. What was the number you got before you did 5 times it?
Oh, 136.
136. So you'd come over here and done 5 times 136 minus the 64, and then that gives you 616. So your work would have looked a little bit different. The equality parts of it would have looked a little bit different, but you still would have gotten 616 as your final answer. All right, this is where I changed something, and it happened this morning because I decided that you need to see an example of this because there was a couple of them I signed inadvertently, although it's perfectly fine for you to do it. Change this so that it says n equal 4 at the bottom. Yours probably say n equal to 1, depending on when you printed them out. If it says n equal to 4, it means you printed it out in the last probably hour. Excellent. Yay, you. All right. So we're going to do it for n equal to 4. You've got a couple of examples in your homework that have that. So that's different, right? What else looks different on this problem? Yeah, it looks like a multiplication, right? We've got something multiplied.
Isn't that the same thing as the before?
Huh?
Isn't that the same thing as like the 5 before?
Not quite, because when you had the 5 before it, it was a constant 5 that never changed. When the n is before it, this n's changing. Yes. So if you'll notice, you do not have any rules that say what happens when these are multiplied. Just like when we did antiderivatives in the last section, right? And you guys encountered that a little bit as you were doing your homework, is that if it looked like multiplication, you couldn't actually work with it until it didn't look like multiplication anymore. Same thing here. So the first thing that we want to do is we want to rewrite this with it distributed out. So this is n squared minus n, right? Okay, pretty good so far? That actually looks like properties that you have, right? You've got a property that looks like something squared. It's the third property. And you've got a property that looks like that, just like I. That's the second property. The only thing here that feels a little bit awkward is that they're using n where we were using I before. And where we have had n, they have 140. It's like notationally it just feels awkward, doesn't it a little? It does to me. Because all of these formulas we had back here had n as a top value, and they're using n over here as those values. And now all of a sudden they've used n in the middle of the problem. So you can do a couple of things. If it doesn't bother you too much, you can just work with it the way that they have. If it bothers you a lot, you could turn where they have the n squared minus n right now into i's. Make them all i's. That's okay. I know. Scary. You could do that. It would be all right. I'm going to deal with it just like it is, and I'm going to actually call this value at the top k for the moment instead, and we'll deal with it like that. So where they have n's in the problem, we're going to have k's. It's one way to handle it. All right. So here's the thing. We're going to separate this guy out. So we're going to separate out the n squared from the n. And we're going up to 140. The problem is that those formulas that we based everything on started at n equal to 1, and this starts at n equal to 4. So in order to use the formulas, I have to start these at n equal to 1. But in doing that, I've added something extra that's not supposed to be a part of this. What have I added?
Summation of 1 to 4 of n squared.
Not 1 to 4,
1 to 3.
1 to 3.
Why did you not do n equal 4?
If I use n equal to 4, I can't use the formulas because the formulas are all based starting with n equal to 1. So we're going to do it, actually, Blaine, you identified exactly what we wanted to do. You didn't realize you were doing it when we did it before. When we were doing this problem, and I said, what would you do if this said n equal to 4 to start with or something, or n equal to 3 or whatever it was I said. And Blaine said, we just take away 5. When I said we would start at n equal, like the bottom, I equal 3. If we started at 3, he'd take away 5. Because he would have taken away the 1 and the 4. Those were the first two terms, right? We just wouldn't have them in the problem. Well, that's actually how we're going to treat this over here. we need to take out the term that's A1, the term that's A2, and the term that's A3, because they're really not there. Because we were supposed to start at n equal to 4. So I'm sort of adding in A1, A2, A3 right here, and I'm taking out A1, A2, A3 over here. It's a compensation is what it is. It's kind of like when you did completing the square. Do you remember completing the square? Parabolas and things, and you added in this piece so that you could subtract the piece on the outside of the parentheses? Or you added something on the left and then you added it on the right to compensate? That's what we're doing here. We're just compensating. And again, the reason we're doing it is because those formulas are all based on n starting at 1. So in order to use them, we have to start n equal to 1. Okay. So the formulas say that what I've got here on the first piece is that this is going to be, and I'm using k times k plus 1 times, 2k plus 1 over 6. And then I have k times k plus 1 over 2. All of this is going to be done when k is 140. It's the top value. But I need to figure out what in the world are A1, A2, and A3 for the original problem. You can either do it from here or from here. I'm going to do it from here. If I plugged in the number 1 into this, what would I get?
0.
That one's 0. Just for the sake of being clear, I'll write it in. What happens if I plug in the number 2 into this? I get 2, right? Because 2 squared is 4 minus the 2 is 2. And what happens if I plug in the number 3 into this? I get 6, because it would be 3 squared, which is 9, minus 3, which is 6. And this is going to happen when k equals 140. So we're going to plug the number 140 into this and see what we get. I've got a blank screen over here. Need a little more space. So we have 140 times 141 times 281 over 6 minus 140 times 141 over 2. And then I've got, what were my numbers? 0, 2, and 6, that's a total of 8, right? Minus 8. Let's see what I have written down. I have 924,490 minus 9,870, and then minus my 8. Do those match up with what you guys are getting? If you do it all in one fell swoop, that's fine too. What'd you get for your final answer, Carrie-Ann? You don't have a calculator. Did someone get to there yet? Did you have one, Ben?
114,612.
Does someone else have that value too?
Yeah.
Sam, yes. Oh, I heard. It was like in unison. Fabulous. So 914,612. All right. Any questions on that?